All right. Well, you saw I had to rearrange the sort of schedule for the course a little bit because I had the fantasy of discussing the logic and the semantics in one session, and it wasn't until last week that I realized that was berserk and that they each needed their own session. So this one is put in for that reason. Last time I talked about two ways, sort of diametrically opposed ways you might think about the relation between reasons and logic. And something like the traditional view, a 20th century view that I call logicism, says good reasons just are at base logically good reasons. What we've got to do is reconstruct our reasoning to show the logical skeleton that's behind it that holds the whole thing up. And I suggested an alternative to that, logical expressivism, that says good reasons are just whatever the reasons are in our non-logical language. We could understand this from a pragmatic point of view in terms of our practices of taking or treating people as entitled to various commitments, or we could understand them in truth-maker metaphysical terms, in terms of the mereological and modal properties of states. However we understand them, we should understand the goodness of non-logical reasons first. And then logic comes on the scene with an expressive task, not to determine what's a good reason, but to let us say that something is a good reason or a bad reason, to let us talk about the reasons that are articulating the contents of our non-logical concepts. And suggested in these terms that the expressivist ideal for a logic is one that's universally LX, universal in that no matter what base vocabulary you start with, it suffices to, the logic suffices to let you make explicit what those reason relations of implication and incompatibility are. And I suggested the principles governing the use of conditionals and of negation, paradigmatically the deduction detachment theorem, or a double Ramsey condition that says that gamma should imply A arrow B just in case gamma together with A implies B. You can see that as a way of saying that. It becomes part of the implicit content of gamma that the implication of B from A is a good one. And I introduced sequent calculi due to Gensen as a powerful kind of meta-language for specifying meta-inferences, for inferences between reason relations. Gensen's idea was to treat implications represented as sequence as the objects of a mathematical system and investigate the relations between them and operations on those reason relations. And I laid out the rules for our favorite system, NMMS, non-monotonic multi-succedent system. And though we didn't look at the proof at all, it's in the book available. This very powerful expressive completeness theorem due to Dan Kaplan that says if you take, in the most interesting direction of it, if you take any implication, any sequent in the logically extended language built on some base. So you've got a set of logically complex sentences as the premise, as the premises, and you've got a set of logically complex sentences as the conclusion. Pick any arbitrary pair like that. This expressive completeness result lets you say what that implication says, in the sense of what base implications have to hold that are necessary and sufficient for this big monster to hold in the extended language. And it doesn't matter that it's a single sequent in this extended language. We can have sets of them too, and still can compute from those what has to be true in the base in order for those sequents to hold in the extension. Necessary and sufficient conditions, we can go both ways. So you know what all the base vocabularies that, when extended, validate this implication, you know what they all have in common. It's this set which we can compute. And the less interesting direction is you can go the other way too. If you pick any set of sequence in the base, you can compute a single sequent in the logically complex language which says that those base sequence hold. If you want this to be bidirectional, you have to play a little bit with the structural condition of contraction. You have to have a contraction-free system in order to do that, so you actually have to work with multi-sets rather than with sets if you want both directions of the theorem to hold. So that's really a remarkable result, I think. I can imagine somebody saying, well, is that so remarkable? Isn't that what I can do in two-valued classical logic with a truth table? That is, if you give me the truth tables for the antecedent of the, think of it as the antecedent of a conditional, the premises of the implication, and for the conclusions, if you're given those truth tables, which we know how mechanically to produce for those logically complex sentences, don't they tell us exactly what they're saying about the truth values of the atomic sentences? Well, yes, that is a corresponding result. It's a very fragile one. That is, that doesn't work in classical logic if the base that you're looking at isn't transitive or isn't monotonic. It doesn't generalize to substructural cases at all. It will determine the implications in the base that hold, but only because it's got such a trivial notion of good implication. That's just anyone that doesn't have a true premise and a false conclusion. But as I said at one point along the way, NMMS is just classical logic under full structural circumstances. What's remarkable about it is that it degrades gracefully. It has an analog of that. It has an analog of that truth tabular property much more generally, and in the substructural cases. And then just to show how our construction relates to some objects of independent interest, I talked about the trilogics, the three-valued logics of K3, strong Kleene, and LP, the logic of paradox, that turn out, when you think about them from an inferential point of view instead of from a semantic multi-valued point of view, just to be the logics of premissory role inclusion and conclusory role inclusion. And we talked a little bit just at the end about why those features show up as the paracompleteness of K3 with truth value gaps, and the paraconsistency of LP with truth value blots. So that's where we got into the end last time. So today I want to think about implication-space semantics. Here's a way of thinking about it. We saw two independent, but ultimately Hlobil shows isomorphic ways of specifying reason relations, material reason relations, of understanding what the snake turnstile can mean when you write a set of premises on the left of it and a set of conclusions on the right of it. One, pragmatically, that's saying the position that anybody's in, if they're committed to accept all the premises and committed to reject all the conclusions, is one they can't be entitled to. That's a position that's normatively out of bounds. That's one way of understanding. That's a thing to mean by implication as expressed in that turnstile. But another thing to mean is that every fusion of any truth maker of all of the premises with any falsity maker of all of the conclusions is an impossible state. That's in alethic, modal, mereological, because of the fusion terms. That's another thing you could mean by implication. And Hlobil showed this remarkable result that if you understand implication in those two ways, we can set up an isomorphism between the reason relations understood pragmatically and understood in that representational truth maker semantic way. But now we could ask, is there a vocabulary, a meta-vocabulary, that will let us talk about what they have in common, that'll divide through by the differences between the deontic normative way, pragmatic way of understanding implication, and the alethic modal metaphysical truth maker way of understanding it. We've set up an isomorphism. Now can we talk about the roles that things play in reason relations in a way that just addresses what's common to them? So it's got to abstract from the differences between commitment and entitlement, acceptance and rejection on the one hand, and possibility and impossibility, truth-making and falsity-making on the other hand. And there is a way to do that. Dan Kaplan developed it looking at Girard's phase space semantics for linear logic, which I considered putting a link to in the website, but I think it's just inviting dust rather than clarity. His semantics looks very different from what it comes to in Dan's hands. So it's that implication-space semantics that I want to talk about today. The idea of it, I think, not that this is certainly not the way Girard was thinking about it, and in a sense it's not even the way Dan was thinking about it, but retrospectively, with the wisdom of hindsight, I think we can see. The idea of it is to do model theoretically what Gensen did proof theoretically. So in his sequent calculus meta-vocabulary, Gensen treated reason relations as objects and mathematically investigated relations among them and operations on them in terms of rules of proof. And what the implication-space semantics does is treat the reason relations as objects, but it treats the relations and among and operations on them, model theoretically rather than proof theoretically. Now, what does that really come to? I mean, there's lots of things that the proofs have a linear meta-inferential order of derivations. There isn't an immediate analog of that in model theoretic terms. But if you think about model theoretic metavocabularies, so just generally, in relation to proof theoretic ones, there are various well-known expressive advantages of the model theoretic metavocabularies for codifying reason relations. Model theoretic semantics is expressively more powerful on the face of it than proof theoretic semantics is. And this has to do with basically finitistic restrictions that are built into the sequent calculus formalism, corresponding to every sentence only having a finite number of elements in it. And this raises cardinality problems in discussing infinite totalities. I think in the end we can see that the trouble is the sequent calculus doesn't have the expressive power to quantify over sets of implications. At least not, its meta-language doesn't allow iterated alternating quantifiers. So in a model theoretic metavocabulary, you can say things like, for any domain element A, if P of A, then there is some domain element Y such that R A Y. So we've said for any element A, there is a Y. There really is no way of saying anything corresponding to that about sentences in the sequent calculus. So one example that we've seen, at least quickly in passing, was when I talked about the subsidiary project of making explicit not just reason relations, but local islands of structure in a base vocabulary. So we say, well, monotonicity doesn't hold generally, but there still are some monotonic implications. From bird to flies, that's not a monotonic implication, but from green to colored still is. From 4 to even still is. And we suggested that we could enrich the expressive power of the sequent calculus metavocabulary by adding to the snake turnstile an upward arrow, where if gamma implies delta with the upward arrow, that means not only does gamma imply delta, but it does so persistently. That is, no matter what other premises you throw in. And indeed, no matter what other conclusions you throw in, remember the conclusions are disjunctive on the right. So, well, that's to add quantificational expressive power. So it can say not only does gamma imply delta, but for any theta, gamma together with theta implies delta. That quantificational expressive power, not native to the sequent calculus setting, you can add it. But what you can't add is the capacity to make arbitrarily complex quantificational claims about sets of sequence. If all of these sequence hold and exactly one of these sequence holds, or if it's the case that whenever one of these sequence holds, one of these sequence holds, then draw the line and draw a conclusion. You can't say anything like that in the sequent calculus metavocabulary. Now, it's remarkable what Gensen could do with the expressive power that he had, but there's no question it's a limitation. And the implication space semantics is supposed to overcome that. It's going to let us use the full quantificational apparatus in the meta language that we use to specify these models. And I want to advertise 3 results that we get. Well, this is an advertisement for where we're going. The first is we can define operations on implications in implication spaces that let us get a sound and complete semantics for NMMS, regardless of what the base vocabularies are. So for NMMS as a universally LX logic, you can give a sound and complete semantics in implication semantics, semantic terms. Second, we can show how to produce an implication space model for any truth maker model and vice versa. That is, we can go back and show how to go back and forth. If you think about the function of models as producing counterexamples to implications, we show that they have exactly the same expressive power. Which is to say that it is the very conceptual roles that truth maker semantics applies to things that are made explicit in the implication space semantics. And then the third result is another isomorphism result that I think should be compared to the Hlobil isomorphism between the right kind of pragmatic metavocabulary and the right kind of truth maker semantic metavocabulary. And that is a mapping of the implication space semantics onto the sequent calculus, so that we can say how any operation in the sequent calculus can be reproduced in the implication space semantics, so that we can mechanically compute the construct the implication space equivalent of any system that we can formulate in the sequent calculus. And this means, we get for free implication space formulations of any logic that we've got sequent calculus formulations of. So, for instance, linear logic, but it's a structural isomorphism that connects algebraic features of the model theory with syntactic features of the connective rules in the sequent calculus. This won't mean a lot just now, but this is at the bottom of page 2 and over under 3 in the handout. You really will need a handout there. So the rules of NMS, this is a quote from the book, are not only equivalent to the semantic clauses of truthmaker theory, they're also equivalent to the semantic clauses of implication space semantics. And we can formulate this correspondence in general as follows. The first elements in the roles defined by the semantic clauses, we haven't seen any of them, so you don't know what those are, correspond to the left rule in a sequent calculus. This is going to be comparing the interpretation function just above that on page 2 with the rules of NMMS. And the second element corresponds to the right rule in the sequent calculus. The roles superscripted with a plus stem from sentences that occur on the left in the top sequent, and the rules superscripted with a minus stem from sentences that occur on the right in the top sequent. And we use 2 operations in the semantics. An adjunction indicates the adjoined roles stem from sentences in a single top sequent, and a simjunction indicates the simjoined roles stem from sentences that occur in different top sequences. So, given that the contexts are always shared in all the sequence of any rule application, this means the semantic clauses uniquely determine the rules of NMMS and vice versa, and not just for that particular logic, but across the board. So, we have here a crucial data point in debates about the relation between proof theory and model theory in understanding meaning, understanding understanding inference and implication. So those are the three things I want to explain. Sounded complete for NMMS. Can go back and forth, find homomorphic, anyway, truth-maker model for any implication-space model and vice versa, and then drawing this deep and fruitful connection between the structure of sequent calculus connective rules and the algebraic conditions in the implication space that correspond exactly to them in the sense of generating the same good implications. So that's all to motivate a little our worrying about all the formalism that you can see where we have in store for us. So what is an implication space and an implication space model? Well, basically, it's just a vocabulary, the way I've been talking about it. I introduced at the beginning the notion of a vocabulary as a lexicon, a set of sentences, together with a set of reason relations. And I suggested we could think of the reason relations just as a set of pairs of sets of sentences. A pair of sets of sentences we can think of as the premise set and the conclusion set, thought of in this multi-succedent way. That is, it's the conjunction of all of the premises that yield the disjunction of all of the conclusions. That's not intuitive, I think, for anybody, but we have the bilateral understanding of it. Oh, that just means that the implication is good if commitment to accept all the premises and commitment to reject all the conclusions, that's implicitly disjunctive, is impossible. And the corresponding thing, if the fusion of any truth maker of all of the premises, that's conjunctive. With any false maker of all of the conclusions, that's implicitly disjunctive, if we think about it in terms of truth values there. So if we think about implications in this multi-succedent way, so each one is a pair of sets of sentences, then our thought was, well, and the vocabulary picks some of those as the good ones. So that's just that set. And we saw that we can encode incompatibilities that way if we say that anything that has the empty set as its second element, what that's really saying is that that set of premises is incoherent, so that any one of them is incompatible with the rest of them. So we can encode them. Now, the only thing that's different, really, with the implication spaces is we make explicit the space. That is, rather than thinking of the first element as, I mean, we can do this either way, but typically rather than thinking of the first element as being the set of sentences, we think of it as the set of candidate implications that that set of sentences generates. That is, as the cross product of the power set of the lexicon, that is, just as the set of all pairs of sets of sentences of the lexicon. Those are all candidate implications. Some of them are good, some of them obviously aren't good. CO tells us that it is the restriction that if the two sets of sentences in any pair have a non-empty intersection, then that's a good implication. Because at least one of the conclusions is also a premise, and so you get the disjunction of the conclusions. So really, implication spaces, have been with us all along in terms of the sort of hand-wavy talk about vocabularies. An implication space model is that set of candidate implications generated by some lexicon, and we'll say a finite lexicon of lexically atomic sentences. So we form the space that consists of all the pairs thought of as premise and conclusion pair, elements of pairs, of candidate implications. And the second element of the model is then some subset of that we say, oh, and those are the good ones. And the whole thing will be CO compliant, that's just an example, if it's sufficient to be in the good set, call that I, the set of good implications, that there's an overlap between the premise set and the conclusion set. If all and only the good implications in the base are those that hold because of CO, NMMS is just going to be classical logic, even in the substructural case. And as long as all the CO instances are included in the good implications, it'll be superclassical. You'll get all the theorems and all the consequences of classical logic will hold as well. Okay, so we have this structure. It's a relational structure. It has a domain and a very simple structure on it. Right? The structure on it is just a subset of, a distinguished subset of the space of candidate implications. What can we do with that in a model theoretic way? And here is the idea that Dan Kaplan had articulated in the chapter of his dissertation that treats this, that I just am in awe of. I know how hard it is to get to this because I've spent my entire adult life wanting an inferentialist formal semantics of the sort we have now, and never got anything like what Dan came up with, because I took it that what an inferentialist does is the same as what other semantic theorists do. You're going to have an interpretation function that assigns some semantically relevant whatsits to atomic sentences, and then on that basis you get to compute an assignment of semantically relevant whatsits to compound sentences formed from them by applying logical operators. And the inferentialism, I thought, comes in that what's the semantically relevant whatsits? What's the semantic interpretant? What is the universe of semantic interpretants from which we're drawing? Well, that should be reason relations. What we should care about a sentence is the implications that it plays a role in as a premise and a conclusion, the incompatibilities that it stands in. So I thought that the way to do an inferentialist semantics was to interpret sentences, but on the side of the interpretant, to look at reason relations, at inferential relations. And it is true, we will look at reason relations as the semantic interpretants. But what Dan saw was the semantics has to start not by interpreting sentences, but by interpreting reason relations. That the reason relations of sentences are actually inherited from relations among the reason relations themselves. And the semantics has to start there. So that inferentialists should disagree with representationalists, not just about the semantic interpretants, about what kind of thing they are, but also about what's in the first instance semantically interpreted. And this is something that I should have known. I'm looking for a quote here. I'm sorry, this is a Sellers quote, and I might as well give you the exact. Yeah. So when Sellers talks about Kant, he says, Kant inherited this logical tradition that was bottom up. You had a doctrine of concepts, particular and universal, and on that basis you built on top of that, out of those raw materials, you build a doctrine of judgments that talked about the form of a judgment in terms of the classificatory structure of the concepts in it. And on top of that, you built a doctrine of consequences or syllogisms. And Sellers says Kant turned that order of explanation on its head. So this is a quote from his early essay, Inference and Meaning. He says, Kant was on the right track when he insisted that just as concepts are essentially, and not accidentally, items which can occur in judgments, so judgments, and therefore indirectly concepts, are essentially, and not accidentally, items which can occur in reasonings or arguments. I mentioned before that elsewhere in counterfactualist dispositions and the causal modalities, Sellers argues that to count as applications of concepts, as having descriptive content, and not just to be labels, linguistic expressions must not just have appropriate circumstances of application, so that it's correct to make that noise under some circumstances and not under others. They also have to have inferential consequences of application. They have to be, as he says, situated in a space of implications. You can't just look upstream at when it's appropriate to utter this, what are the assertability conditions of it. You have to look downstream at what the consequences of it are as well. In making it explicit, I elaborate this Damatian model of circumstances and consequences of application, suggest that, well, anyway, the next step in articulating it is to distinguish, to split up the notion of propriety. When we talk about the circumstances of appropriate application and the appropriate consequences of application, that's how one sorted, is it appropriate or not? And we've seen if you split that into a bimodal deontic vocabulary of commitment and entitlement, you can get a lot more. So think about what the consequences are. What do they commit you to? What do they entitle you to? And on the circumstances, which circumstances entitle you to this claim? Which ones commit you to it? We go on from there. But Sellers is emphasizing in that essay, where he talks about the sentences needing to be situated in a space of implications, those need to be subjunctively robust implications. So, to remind you of this little bit of business, we say, to grasp a concept lion, say, you have to divide material implications and incompatibilities involving it roughly into good ones and bad ones. I say roughly, you got to make some such distinction, however fallibly and perhaps incorrectly and incompletely, but you got to have some distinction between the good and the bad reason relations it stands in. And furthermore, you have to have a view about which of those would still hold, would still be good if some features were changed about it or some new information were added to it. That is, you need to have some practical grasp of the range of subjunctive robustness of the goodness of those implications. And that's what we're going to focus on in the implication-space semantics. That is, we've got a kind of extensional content for candidate implications. We have our space of candidate implications generated by some lexicon. That's the space of all pairs of sets of sentences of the lexicon. And we have a distinction of those into good ones and bad ones, because we have our distinguished set, I, of the good implications. So that's like a truth value for candidate implications, saying some of them are good. It's a goodness value rather than a truth value. Some of the implications we're taking to hold, those are good implications. What do we mean by that? Well, I can tell you a bilateral pragmatic story about what I mean by that, or I can tell a truth maker story about what I mean by that, by good. Those are actual explanatory theories. They say, let me tell you what determines which are the good ones and the bad ones. But now we're abstracting from those stories and just looking at the distinction. But that's like an on-off 1-0 true-false semantic evaluation applied not to sentences, but to candidate implications. Are they in the privileged set or are they not? Are they good ones or not? That's the goodness value of them. But to do any useful model theory, you need to define intensions from that, not just extensional contents. And for that, we look precisely to the range of subjunctive robustness of an implication. And by that we mean we have an implication, gamma turnstile delta, and it's either good or it isn't. Let's say it's a good one. Well, grasping the range of subjunctive robustness of that candidate implication is knowing which of its neighboring candidate implications are also good if this one is good. What additional premises could you throw into this good implication without infirming it? Those are the premises that go in the range of subjunctive robustness of it. So if we say, the lioness, the hungry lioness, if she notices the wounded wildebeest, will chase it, and we say, well, that's a good implication, but it's defeasible. If she's struck by lightning, she won't. And if you know about lions, you probably would reject that implication. But it would still be good if the beetle on that branch on a tree a mile away had climbed a little bit farther up. That wouldn't make any difference. If it were a Thursday instead of a Wednesday, that wouldn't make any difference. You got a sense of what additional premises you could throw in order to keep the good implication good, or to generalize that for some implication that is not good. What would it take to make it good? What additional premises do you need to add to what you've got here in order to get that conclusion that you don't get right now? So, we can associate with each candidate implication the set of all implications that you can get by putting supersets of its first and second element, by adding more premises and adding more conclusions. Doing that is strengthening the premises and weakening the conclusion, because it's disjunctive on the right. So if you look at the handout, the range of subjunctive robustness, the RSR, of a candidate implication is the set of sentences that can be added to it. And what we mean now is, what can we add to X and what can we add to Y? So that's what other candidate implication can we combine with this to solve a consequentiae, that is keeping the goodness of the inference. So we're going to be taking another candidate implication, which is some more premises, some more conclusions, and we're just going to add those, set theoretically union those. And now the range of subjunctive robustness of an implication is all the implications like that that are good. All the additions to the candidate implication that you started with that yield a good implication, one that's in the distinguished set I. It's much easier and more intuitive to just think about the premises and say, and you can do the same thing with the conclusion. Range of subjunctive robustness, what other conditions would not infirm this inference or would make it a good one? It turns out to be useful to keep that in. And we're just going to treat the intention, the semantic value of a candidate implication, as the set of candidate implications that, when combined with it in this particular way, yield a good one. Its range of subjunctive robustness. And now we're going to operate on those ranges of subjunctive robustness instead of on the candidate applications. That is, we're going to do semantics with them. So, the first thing you'd look at is two candidate implications such that the range of subjunctive robustness of one of them is included in the range of subjunctive robustness of another one. Here's, if you think about this in terms of intensions and extensions, one's interested in how you can compute the extension from the intention. In possible world semantics, you need to add some argument that you apply the function that is the intention to. So what corresponds to an extension for a sentence in this is truth at a world, and the intention is a function from worlds to the values of that proposition at that world. Does it hold there or not? In this case, what can we say about how can you recover the goodness of a candidate implication from its range of subjunctive robustness? That is, if you're just given the range of subjunctive robustness of some candidate implication, how can you tell from that whether it's a good one or not? Well, all and only the good ones have the pair of the empty set and the empty set in their range of subjunctive robustness. That is, if you do nothing to the premises and the conclusions, it'll give you a good implication. If that's true, if that minimal candidate implication, if that's in the range of subjunctive robustness, that's true of all and only the good implications. So in this setting, for evaluating implications now, not sentences yet, the sentences are still buried in there. We use them to build this structure, but we're not semantically interpreting them yet. But in that structure, where the extension of a candidate implication is whether it's good or not, whether it's in the distinguished set I, and its intension is its range of subjunctive robustness, if you're given the intention, you can determine the extension. Don't need to evaluate it at a point or anything like that. So this remarkable idea of Dan's was that to bring off an inferentialist semantic model theory, one should listen to Sellers's Kant and think about the meaningfulness of the implications first. Do your semantics for them. Anyway, do an initial level of semantics that is semantically interpreting reason relations or candidate reason relations first, and then appeal to that to get the sentences. In 40 years, this never occurred to me. And Dan looks at it and says, do this, and now this thing comes. So, it says that on the handout on your first page. If we're understanding the intentions, the meanings, the semantically relevant whatsits that we associate with implications, if those are the RSRs of them, which are just sets of implications, the RSR of any implication or set of implications is just a set of implications, then we can say that two sentences are implicationally equivalent if they have the same RSR, the same range of subjunctive robustness. And we can then, having the same range of subjunctive robustness is an equivalence relation, it's reflexive, symmetric, and transitive. So we can define equivalence classes of implications now and say, well, these implications are implicationally equivalent if they have the same range of subjunctive robustness. So it might be that given what the meanings of the sentences are, that some of our candidate implications are, as it were, syntactically different. They have different sentences. They are different pairs of sets of sentences, but if they play the same implicational roles, we don't care about those differences. Those are not going to be semantically significant differences. So from now on, we're just going to care about those roles. And already we will have risen above the distinction between the normative pragmatic metavocabulary and the truth-maker vocabulary. The Hlobil isomorphism shows that the implications can line up between those. So the ranges of subjunctive robustness of those implications can line up. And now we don't care about the difference between something that is specified in the pragmatic metavocabulary and something that's specified in the truth-maker vocabulary if they're in the same equivalence classes of ranges of subjunctive robustness of candidate implications. So we've already gotten to a more abstract level. And here, I mean, it's worth saying this, though it's a very elementary point. This is abstraction in a specific technical sense, the one that Frege was the first one to get clear about in the Grundlagen, where he says, he compares relatively concrete things, Euclidean lines, and we have a relation among them, relation of being parallel, which is an equivalence relation. It's reflexive, every line is parallel to itself. It's symmetric, if A is parallel to B, B is parallel to A, and it's transitive, B is parallel to A, and C is parallel to B, and C is parallel to A. And that means we can take equivalence classes of lines under the equivalence relation of being parallel and introduce a new object, a new kind of object that's abstract relative to the lines, namely the directions of lines, where we say, if these two lines are parallel, we can now say they have the same direction. Well, that direction is just the equivalence class of parallel lines that they're in. And it's worth keeping that model in mind. That's how you move from a more concrete specification of the line to an abstract one, the specification of the direction. And that's exactly what we're doing here. We start off with objects that are individuated by the sentences they contain, the candidate implications, but we define the notion of range of subjunctive robustness from them, appealing to the other element of the implication space models, namely the distinguished subset I of good candidate implications. We define range of subjunctive robustness and then point out that having the same range of subjunctive robustness is an equivalence relation, and so we can introduce these new objects, which are not the implications themselves, but the role that the implication is playing with respect to ranges of subjunctive robustness, what we'll call implicational roles, but these are implicational roles of implications now. So far, though we generated all this from our lexicon of sentences, none of the definitions that I've given, well, that's not true. We do, in defining range of subjunctive robustness, we do appeal to the set theoretic character of these things. But it's open that two candidate implications that are quite distinct could have played the same implicational role here. Okay, there's one more thing we can do before we move to step 2 and look at sentences, and that is define operations on now implicational roles, but they're basically operations on ranges of subjunctive robustness, and we know at every stage how to translate those into set theoretic operations that appeal to the distinguished set of good implications. And so here at the bottom of the first page of the handout are two operations on, now I've just shown them as operations on individual candidate implications, but it really should be, but just, or this way to leave out a bunch of funny parentheses on things. But the idea is, in effect, we already used the notion of adjunction in defining range of subjunctive robustness. That is what we do in adjoining two candidate implications is take the union of their first elements and the union of their second elements. Now we're going to do that with the equivalence classes under the ranges of subjunctive robustness of these things instead. And so there's a little fussing to do, but conceptually it's, I hope it's clear. That's a way of combining candidate implications or their implicational roles. And it's a kind of union of them. If you think that that's how we add another candidate implication to this one to determine whether it's in the range of subjunctive robustness of the base one by whether the result is in I, the set of good implications. And we introduce another one that corresponds roughly to intersection rather than to union. The simjunction of two candidate implications or their implicational roles, strictly their implicational roles, is whatever has the range of subjunctive robustness that is the intersection of the range of subjunctive robustness of the simjoined things. So that if xy is the first simjoined thing and zw is the second one, we produce something such that that its range of subjunctive robustness, what you can add to it and get a good implication, is anything you can add to the first one and get a good implication if you can also add that same thing to the second one and get a good implication. So the range of subjunctive robustness is just the intersection of those two ranges of subjunctive robustness. So to write this down precisely, well, is a little bit of fussing, but the idea of it should be clear. We basically just have an operation that corresponds to unioning the ranges of subjunctive robustness and one that corresponds to intersecting those ranges of subjunctive robustness. Okay, remember, we're doing all of that in the semantics of interpreting implications and doing these operations. So now at the second stage, but only at the second stage, and this is quite unlike any semantics I've ever seen before in going in these two stages, now we're going to worry about semantically interpreting sentences. And the thought here is to parallel in the sentences what we just did for the implications. Because for the implications, we have a premissory part and a conclusory part. That's what a candidate implication is a pair of a set of premises and a set of conclusions. Well, what we want for a sentence is to mimic that. We want the role of the sentence to be the role it plays as a premise in implications, first element, and the role it plays as a conclusion, second element. And now we know we're going to do that using ranges of subjunctive robustness. So how can we think about the role that a sentence plays as a premise, well, consider the range of subjunctive robustness of the candidate implication. Suppose our sentence is A empty set. The range, so A occurs as the only premise, and we've got no conclusions. Now, what's in the range of subjunctive robustness of that is anything that if you add to that, you get a good implication. Well, the result of doing that is going to be just whatever you added together with A. We're just adding that as a premise. So the range of subjunctive robustness of A is just the set of all the good implications in which A occurs as a premise. Well, minus A, but it determines that set. And similarly, for looking at the range of subjunctive robustness of the candidate implication whose first element is the empty set and whose second is the sentence A. So we can talk about the implicational role of A as just being the range of subjunctive robustness of that candidate implication with it as a premise, together with the range of subjunctive robustness of that candidate as a conclusion. And here, we make a move that in some sense, we don't know what we're letting ourselves in for by doing this. I'll say something about that in a minute. We say, okay, what we're getting as the implicational role of a sentence is a pair of sets of implications. We could generate a space of all possible sentential contents, implicational contents, as just the set of all pairs of sets of implications. Each one of them is, as it were, a candidate for being the meaning of a sentence. And what I had in mind with my cautious remarks just a minute ago is we really have not explored what kind of monsters inhabit that space of potential interpretants of sentences. You know, we can say what the well-behaved ones are like, but how many different kinds of badly behaved ones are there? There's going to be a bunch of them. What sorts of structural conditions have what effects on the behavior of things? You know, we're going to give you a set of rules for the ones that act right, but we really have not explored the pathologies of these potential things to mean by sentences. I'll give an example of some of the pathological ones below, but here is a rich area for investigation of kinds of pathological meanings, pathologies of meaning. And it may be that some of them are so pathological that we should have a much more restricted space, a much more restricted superset of the good ones that we'll talk about. Okay, then here's the first punchline. In the middle of page 2 on the handout, here are, here's an interpretation function that assigns conceptual roles, pairs of sets of implications, to the sentences of the language. So if A is an atomic sentence, then we'll put square brackets around it to talk about its semantic interpretant, and that's a pair, an ordered pair of its premissory role, which we mark with a plus, and its conclusory role, which we mark with a minus, and those are the ranges of subjunctive robustness of its canonical representative, a empty set for, so little a plus in this formulation is the range of subjunctive robustness of the candidate implication a empty set, and a minus, the second element of the interpretant of A, is the range of subjunctive robustness of empty set A. And now we're going to show how to extend that assignment of implicational roles to atomic sentences to the sentences that we get by applying logical operators to them. And you can just look at these to begin with. The intersection, the square sort of intersection symbol is simjunction. The square union symbol is adjunction. These are the right definitions. I'll say something about why they are, but you can just look at this. It was not easy to find these. We have our operations on the syntactic side. What they have to give us is what's on the facing page. In the middle of page 3, I've reproduced the sequent calculus definitions of the connectives. And the soundness and completeness proof is going to show that you get exactly the same good implications semantically using these definitions that you get proof theoretically in the sequent calculus. And furthermore, they'll show us how you could start with the semantic characterization, and if you know the rules, write out the sequent calculus definitions, and vice versa. You can start with the sequent calculus ones and just write these out. Now, this is what it looks like when you finally understand how everything works. Believe me when I say these were not easy to find. And I didn't do this work. This work Dan and Wolf did. Motivated and inspired by Girard, but they figured this out. So I want to say some more about, to try and make this, I don't know, a little bit intuitive, if that. So I suggest a little exercise here. Not that you should be worrying about this now, but if, in a cool twilight hour, if you decide to do it. Once you understand these things, I just translated tonk into our notation tonk, the connective that has the left rule of disjunction and the right rule of conjunction, and so lets you go from A to A tonk B the way you can go from A to A or B, and then lets you go from A tonk B to B the way you can go from A and B to B. Well, we can say what that conceptual role is in terms of ranges of subjunctive robustness, this is how to compute the range of subjunctive robustness of A tonk B from the ranges of subjunctive robustness of A and B. And I'll say these rules, the ones that I pointed to before that are at the bottom of page 2 going over to page 3, the rules for going back and forth on this are sufficiently robust that, we have sequent calculus formulations for all the connectives of linear logic, for instance. Well, then we could just, and did do, Wolf does in the book, just give you the implication-space semantics for multiplicative and additive linear logic. That comes for free with this translation. Let me say another word about other logics. Intuitionism, remember, you get in the sequent calculus by taking the same rules, so it could be the NMMS rules, but only allowing a single conclusion on the right side of the turnstile. So sometimes multi-sextant proof theory is called set-set proof theory as opposed to set-sentence proof theory, which is the one that only allows single succedents there. And Gensen proved this remarkable result that the very same rules that give you classical logic in a multi-succedent setting give you intuitionistic logic in a single succedent setting. You can use the same rules for negation, the same rules. And this was an eye-opening feature. Well, we have a single succedent version of NMMS, NMSS, non-monotonic single succedent, and indeed Wolf came up with that first before Dan realized the advantages of going to a multi-succedent setting. And you can do a version of implication-space semantics, taking your candidate implications not to be pairs of sets of sentences, but ordered pairs of a set of sentences and a sentence. If you're interested in going back and forth, you might want to think of that as a singleton set containing the sentence. But that's your space of candidate implications, and you can do analogs of our various operations on it. We have not explored this. That implication-space semantics is terra incognita. For instance, we don't have soundness and completeness proofs of things with that semantic setting. So much being, so little time. But it's clear that there are results to get there. They're not going to be as pretty or as smooth as the multi-succedent ones, but something can be done there, and we haven't done it. So I'll just mention that. And as far as the generality of this kind of semantics is concerned. But to try and get some sense of what these things mean using the simjunction and adjunction, the negation is pretty easy, right? It just flips the premissory and conclusory roles. So the range of subjunctive robustness of not phi, of not A and the empty set is always just the same as this range of subjunctive robustness of the empty set and A, and vice versa. So whatever yields a good implication when combined with not A empty set also yields a good implication when combined with the empty set A. That's how it lets us make explicit incompatibility. For we encode the fact that a set of bearers gamma is incompatible with phi in our implication as gamma union phi empty set is in I, is a good implication. And the negation clause precisely ensures that you can substitute the negation for the negatum on the other side, salva consequentiae. That is, that gamma union A empty set will be in I, just in case gamma not A is in I. So negation makes explicit on the right side of the implication that it's ruled out by what's on the left. And that's what we wanted. That was our condition, the incoherence incompatibility property. We wanted gamma to imply not A, just in case A was incompatible with gamma. And that's what flipping the premissory and conclusory role does. I think that's intuitively important for seeing how the premissory and conclusory sides can line up with truth makers and falsity makers in the truth maker setting. Though thinking about the two definitions of implication, why the condition in truth makers is that the fusion of any truth maker of all the premises with any false maker of all the conclusions is out of bounds, is an impossible state. That's also telling you how the falsity is connected to the conclusory role rather than the premissory role. Okay. I hope that's semi-intuitive about negation. The conditional is harder, but here's a story. The content of the conditional always has as its conclusory role the adjunction of the premissory role of the antecedent and the conclusory role of the consequent. Now, that's not intuitive, but we're talking about the conclusory role of A arrow B, which you see is A plus adjoined to B minus. And A plus and B minus. And if you look at the right rule for the conditional, you'll see that to get the conditional below the line, so we're always the meta implications are going down to the line. There's a way to go back up, but this rule is going down, and it's got A in its positive role and B in its negative role. That's what we want when adding A to gamma adds B to the conclusion. That's what it should be to have gamma imply A arrow B. So that conclusory role is just what we want in order to get that conditional, that feature that makes the conditional mean what we want it to mean, to codify in some statement as implied by just the sets where adding the antecedent as a premise would give you the conclusion, would give you the consequent as a conclusion. The premissory role that an interpretation function assigns to a conditional, so now you're looking at that mess before the comma, is the adjunction of the premissory role of the antecedent and the conclusory role of the consequent. That doesn't look right. Oh, sorry. That's what I was just talking about. Sorry. And the premissory role, that messy thing, is the simjunction of the conclusory role of the antecedent, the premissory role of the consequent, and the adjunction of those two roles. It's the simjunction of them and the adjunction of them. That's what we get. There. Yes. So, the range of subjunctive robustness of gamma union the conditional AROB delta is always the intersection of the range of subjunctive robustness of gamma, comma, delta union the antecedent and the range of the subjunctive robustness of gamma union the consequent, comma, delta, with the range of the subjunctive robustness really of both of them. Well, I guess I don't know how to make that more intuitive except to indicate, if you look at the NMMS left rule, and ignore the third sequent above the line, then you've got the standard Gensen rules for the conditional, that you can get that gamma together with AROB implies delta, if gamma implies delta and A, and gamma together with B implies delta. Now, that's not a terribly intuitive conditional rule, it's just the right one. I mean, that's the conditional rule of classical logic in sequent calculi. And in our setting, we have to throw in that adding gamma as a premise doesn't infirm the implication of A, because we need to deal with non-monotonic cases. That's what that third condition says. Yeah. Well, so look, the simjunction and conjunction, these are the right rules. They're the translation into this setting of the standard sequent calculus rules for classical logic. As I say, our version gives you that. It's super classical if the good implications include all the ones with non-empty intersections of the premises and conclusions of the candidate implications. If you restrict the good ones to that, you just get classical logic. Otherwise, you get something that's super classical. As I say, a job of work to come up with these definitions, but it ought to be enough if the raw materials for these are intuitive enough. It's just the notion of ranges of subjunctive robustness of candidate implications. We use that to get equivalence classes of things that have the same ones, and then these are operations to combine those ranges of subjunctive robustness to get the ranges of subjunctive robustness that will assign to new sentences that we didn't have before, to the sentences that are formed using the logical connectives. Okay, so I put these, the NMMS and the interpretation function on sort of facing pages so you can stare at them. The relation between them is in between, that the first element in the roles defined by the semantic clauses corresponds to the left rule, the second element corresponds to the right rule. The roles superscripted with a plus stem from sentences that occur on the left in a top sequent, those with minus that occur on the right. Well, that's a premise and conclusion. That's what they ought to be capturing. An adjunction indicates the adjoined roles stem from sentences in a single top sequent of the sort that you get, say, for the left rule for conjunction. And a simjunction indicates the simjoined roles stem from sentences that occur in different top sequence. So those roles are enough to show how to go back and forth, not just between NMMS and this interpretation function, but between anything that you can write on either side. You can go back using these rules. So we still await a thoughtful extraction of consequences for the various debates that there have been about the relative merits of proof theory and model theory. In one sense, model theory is more expressively powerful than proof theory. In another sense, model theory is cuts less fine. It's extensional in a way in which model theory is intentional. That is, model theory will tell you that something's a theorem. Proof theory tells you why. It gives you the proof, the argument for it, rather than just the verdict on it. But this result is so new that we have not really thought through how that discussion about the relation between model theoretic and proof theoretic codifications of reason relations looks different in the light of this. Okay, it's time for us to take a break if we're going to get one. Let's come back at 2:48. Okay. Well, are there questions or comments at this point? You can tell my view is that you don't need to get all the way into the weeds in order to see what's been accomplished. You have to sort of take my word for it when I say that interpretation function generates a sound and complete semantics for NMMS. But I hope that my discussion in the handout gives you enough to go on that if you really want to see whether that is true, you can go to the book and interpret the careful statement of it there. Yeah.
In implication-space semantics, you've got extension and intention, and then there are all of these sort of equivalence results between what you do with implication space and truth maker and all of that. But truth maker semantics also has a notion of hyperintention. Is there a conjugate notion in implication space, or are we just are we demonstrating that we can do without it?
No, absolutely. If you want to go hyperintentional in the way that Kid Fine goes hyperintentional, so basically you're dropping some De Morgan equivalences because not all the distribution principles of disjunction and conjunction over particularly negation hold. Some of them don't. And one of the things he's pleased about, proud of, is that logical statements that are equivalent in classical logic can be given different meanings in truth maker semantics, so that you can see how you can see what needs to be true for what the world needs to be like for one of them to be true and the other not true. And we can reproduce all of that. Anything you can do, any reason relation you can specify in the truth maker setting, you can specify the same one in the implication-space setting, and indeed there's a mechanical way of doing that. I mean, that's here. We can look at that. So this is bottom of page 3 on the handout, defining implication space frames from modalized truth maker state spaces. So if you start with one of Kit's things, we can define an implication frame for any modalized state space. That's a set S of space of states, a set of possible or impossible states. This is a source of confusion. It obviously doesn't matter. The one is the converse of the other, but sometimes it's done one way, sometimes it's done the other. And then so that's the modal notion, which are the impossible states. What's the partition between the possible and the impossible ones? And then a fusion relation or a part-whole relation, mereological. We know how to go back and forth between those. So how do we get an implication space semantics from it? Well, let the bearers, the things that correspond to points in our set of candidate implications, be worldly propositions, that is, pairs of sets of states from S, and define the good implications by appeal to impossible states in the way Hlobil showed. Then we just do our abstraction. We calculate the ranges of subjunctive robustness of those, shrink them by the abstraction step according to the equivalence relation of having the same set. And as he says, it follows from Theorem 79 that if there's a truth maker model in which exactly a particular set of implication holds among the interpreted sentences, then this construction will give us an implication space model in which exactly the same implications hold. And we can go in the other direction. In the book, we say less about this, but if you're given an implication space model, we can construct a truth maker model that codifies the same consequence relation. Here, let the set of states be the set of pairs of sets of sentences. So we're basically taking the candidate implications to be the states that we're using, and define the mereological part-whole relation from which we get fusion by saying that if one of the states, which is a pair of sets of sentences x, y, and the other one is w, z, we say the one is contained in the other in the mereological sense if x is a subset of w and y is a subset of z. If they're the premise set of the one is included in the other, and the conclusion set of the one. And then say that it's a possible state if we're using the that xy is a possible state if it's not in our set of good implications. Then worldly propositions become pairs of sets of states that is, potential truth makers and falsity makers, which are interpreted here as pairs of sets of pairs of sentences, so pairs of our items. And we impose Fine's exclusivity on those pairs. As we say, each worldly proposition, it has to be that any truth maker of its first element, when fused with any falsity maker of its second element, is an impossible state. That's his way of getting the truth makers and falsity makers to exclude one another. That's what Wolff relied on to define implication, and then consequence is just his definition. So you can absolutely go back and forth between truth maker, mereological modalized state spaces on the one hand, and implication spaces, implication space models on the other. This raises a question from the implication space point of view to the truth maker semantics, which is often differences between states will make no semantic difference in the truth maker framework. In stating their interpretation function, you're assigning to each sentence a set of exact truth-making states and exact false-making states. And it's often the case that there are pairs of states such that you can put the one in as truth makers and false makers and systematically substitute the other for it, and it doesn't change any of the consequence relations among the propositions. Now, this is nothing, we don't even need to worry about the language, just the consequence relation among the propositions can be robust under substitution of some states for other states. Those states are semantically indistinguishable. They're only metaphysically distinguishable. In the metaphysics, you said, these are my states. And in order to do our semantics, we've said, well, what I really care about is pairs of sets of states that exclude one another in a certain way, that the fusion of any state from the first element with any state from the second element must be an impossible state. That's the exclusivity condition. That's what we're interested in. Those are the worldly propositions, and they stand in various reason relations to one another. But there are all kinds of differences, particularly if the state space is uncountably infinite. There are going to be lots of pairs that you can substitute one for the other, salva consequentiae. And we want to say, well, how are we to understand what you mean when you talk about these differences of states? What's the basis of your confidence that you can talk about these differences that in principle don't make a difference to anything that you can say? Isn't that your metaphysical metavocabulary going on vacation? Relative to sort of your own semantics. That is, don't you need a metavocabulary for referring to these states? And how exactly is that done? At some point, the differences have to come out in the reason relations. Well, I think Kit's response is, well, so much the worse for your semantic rationalism. There are metaphysical differences that don't show up there. And my semantic story about them is my truthmaker semantics. That's the story, and comes with a metaphysical story. The claim is that that can't be the semantics of his metaphysical metavocabulary. Anyway, that's a question, an issue that's raised by this result. But we can go back and forth between these settings. And this means, by the way, that we can give an implication space semantic treatment of pragmatic metavocabularies because they specify reason relations and so on. One last observation. Talked last time about premissory and conclusory role inclusions. K3 is the logic of the premissory role inclusions. LP is the logic of the conclusory role inclusions. As you would expect, the home language game of role inclusions is implication space semantics. It gets us conceptual roles. Those are the equivalence classes under under the equivalence relation of having the same range of subjunctive robustness. So if you look in the middle of page 4 on the handout, if as before, A, the conceptual role of A is the ordered pair of its premissory range of subjunctive robustness and its conclusory range of subjunctive robustness, that is, the range of subjunctive robustness of A, comma, empty set and of empty set, comma, A, and similarly for B, then A's is premissorily role included in B, just in case A plus is a subset of B plus, and A's conclusory role is included in B's conclusory role, just in case B minus is a subset of A minus. Those facts offer, in effect, a recipe for interpreting the three-valued logics for giving a semantics for them in this setting. Would have been much easier to make the arguments last time if we already had a general way of talking about implicational roles, which are conceptual roles. We want to say roles with respect to reason relations. Well, what I want to close by saying is think about the relations of these different vocabularies that we've got. We've seen truth-maker theory and implication-space semantics. We can go back and forth from the one to the other. We can use the implication-space semantics to understand sequent calculus. This means, just by transitivity at this meta level, that if you give me anything in a sequent calculus formulation, I can give you the implication space semantic equivalent of it and then translate that into truth-maker semantics, which means we have a recipe for giving a truth-maker semantic version of anything we can write a sequent calculus set of rules for. And that's not something that the current literature allows. Furthermore, the implication space semantics lets us abstract precisely from the differences between the normative pragmatic bilateral pragmatic metavocabulary and the truth-maker pragmatic metavocabulary. They each offer an explanation, an account of what that not only determines what the good implications are, but says in what sense they're good. Like we have the pragmatic sense that anybody who's committed to accept all the premises and reject all the conclusions is not entitled to that holistic position, to that whole position. And on the other side, saying no speakers on the second one, it's saying the implication holds between these worldly propositions if the fusion of any statement, of any truth makers of all of the premises with any falsity makers of all the conclusions is an impossible state. That appeals to all this metaphysical vocabulary. The pragmatic one appeals to notions like commitment, entitlement, acceptance, rejection, and so on. But the implication space semantics abstracts from all of that. And indeed, it says, all I need is the reason relations of the base vocabulary. I can elaborate the space of candidate implications from that, and qua implication space semanticist, I just look at all the assignments of some proper subset as I, as the set of good implications. We can say that the pragmatic and semantic, truth makers' semantic meta-vocabularies for explaining the notion of good implication, specifying a sense of good implication, those are extrinsic meta-vocabularies for articulating the reason relations of a base vocabulary, in that they look to something other than those reason relations themselves, to what people are committed and entitled to and the norms governing that, to what states, when fused, give you impossible states, and so on. The implication space only appeals to the reason relations. Give me the vocabulary in the sense of the lexicon and the set of reason relations, and I'll give you a semantics here. It's not explaining what it means by good implication, because it's taking that over. If in whatever you mean by good implication in the base, whatever you mean there, here's what implications hold in that very same sense in the logical extension of it. And we're giving you semantics of both of those. So the pragmatic and truth maker semantic model theoretic meta-vocabularies are bring in stuff that's extrinsic to the reason relations that they explain and articulate. And they seek to give substantive explanations of the reason relations, saying what they mean by good implication. The implication space meta-vocabulary is intrinsic in that all it cares about is the reason relations of its base vocabulary. It doesn't appeal to anything outside of that. And accordingly, it's not undertaking an explanation of the notion of reason relation of implication or incompatibility. It's just letting you talk about it. It's explicative rather than explanatory. And so is the logical vocabulary that's introduced by sequent calculus meta-vocabulary. The sequent calculus meta-vocabulary takes as input just a set of reason relations. Give me a set of sequents. Those are good in whatever sense you mean good, and I'm giving you rules that tell you if those are good, then according to these rules, these other things are good. And we've seen in that way how to introduce logical vocabulary in a way that makes it able to make explicit reason relations. That combination, the logical vocabulary is not strictly a meta-vocabulary. It's introduced as an extension of the object language. The meta-vocabulary in the vicinity is the sequent calculus meta-vocabulary, but it's intrinsic and explicative rather than extrinsic and explanatory. And we've seen all sorts of relations among these metavocabularies. The Hlobil isomorphism between the two explanatory metavocabularies, and then the relation between the implication-space semantics and both of them in its characterizing the conceptual roles that are explained by, conferred by the reason relations that are explained by those theories. And we've shown, in showing the soundness and completeness of the implication-space semantics for the logical vocabulary, we've shown that the right reason relations are also expressed by that logical vocabulary. In some sense, the logic is what ties all this together. That's what lets us show the equivalence of implication-space semantics and truth-maker semantics, which is our way to get to the pragmatics. In another sense, it's the implication-space semantics, which is a pure language, a pure vocabulary of conceptual roles, an abstract theory of conceptual roles as such. So I want to close today by reminding you of what I said in our very first meeting, that I'd be putting on the table a notion that's familiar in many ways, but specified in unfamiliar ways as well, the notion of reason relations, more specifically of implication and incompatibility, as codified in a vocabulary. But that this topic, reason relations, we'd really only understand in virtue of understanding the relations among metavocabularies that let us specify those reason relations, that let us specify the reason relations of base level vocabularies of whatever kind. And here we see that there's at least these four different but intimately related kinds of rational metavocabulary. The explanatory ones, substantive, that their own vocabulary involves all sorts of stuff that is not reason relations. Talk of states, talk of impossibility, talk of fusion, talk of commitment and acceptance, preclusion of entitlement, and so on. And the two intrinsic explicative, essentially explicative rational metavocabularies, that is, metavocabularies for discussing reason relations, either in an explanatory or an explicative way. And what I want, when I'm being most careful to mean by reason relations, is whatever plays this complex role with respect to these four kinds of rational metavocabulary. What is that role? Well, that it can be explained either in a truth-maker semantic way or in a normative bilateral pragmatic way, and that it can be explicated, made explicit, logically by vocabulary introduced by sequent calculus rational metavocabularies, that is, metavocabulary for talking about reason relations, sequence, and by the implication-space metavocabulary. Anything that plays those specific roles with respect to those four broad kinds of metavocabulary, that's what I mean by reason relations. So, put a general notion on the table in the beginning, but now we're in a position to be really clear and careful about it. And each of those meta-vocabularies gives us a kind of traction on it, gives us an expressive route to that crucial topic of reason relations. And along the way, we've seen issues such as, I don't know, the relation between language and world. In the Hlobil isomorphism, so we've seen that the reason relations have worldly metaphysical correlates and have normative social practical correlates. They are made explicit, just as the logistical tradition wanted us to, by logical vocabulary and by semantic vocabulary, model theoretic semantic vocabulary, but of the implication space kind rather than the truth value, rather than the truth maker kind. Now, surely there are other ways of specifying these reason relations. Almost everybody who's been exposed to the idea of the reason relation says, well, okay, you do this in sort of meatball set theoretic terms. What does it look like in category theoretic terms? How do these reason relations relate to the sort of types that intentional type theory deals with, or, you know, God help us all, homotopy type theory? These are powerful mathematical meta-languages, and the structures that we're talking about of reason relations are really not that complicated. But philosophically, they're resonant. I mean, I say they're not that complicated. I mean, it's not like we can write down the reason relations for any non-logical expressions, any real-world expressions. Presumably the structures that are the reason relations of our talk and our world, ideally those can come to be isomorphic. Presumably those have got a lot of, well, they have a lot more sentences than our computer models are comfortable working with, that's for sure. But still, set theoretically, they are not complicated. And so there's work to be done, there's stuff to be understood by applying these much more powerful meta-vocabularies for describing structures like that than we have. And that's, well, so much being, so little time. That's, at least it should mean that nobody's ever bored again. Okay, well, in a way, this concludes my presentation of the book. I've covered most of the material in it. You should be able to read the concluding chapter now, for instance, and know what's being talked about at every point in it. What I want to do in the rest of the course is talk about the stuff that we don't talk about in there. In particular, next week I want to revisit the pragmatics, because now we see the question of what it is for us to get on top of a set of reason relations so that we're keeping score on each other's commitments and entitlements, acceptances and rejections, in accord with a determinate set of reason relations. How is it that that happens? What does that look like? The pragmatics, as we looked at it so far, just took a snapshot and said, well, if the norms governing the community are that these constellations of commitments are out of bounds in the sense that you're precluded from joint commitment to them, then these other ones are, and so on. But what is it for those norms to be in play? And I want to look at the social dimension of discursive practice, in particular the fundamental distinction of social perspective between attributing a commitment to somebody else and acknowledging it or undertaking it oneself, which is an essential structure of the pragmatic implementation of or version of reason relations that does not have an analog in truth-maker semantics or in implication-space semantics. It's about our connection to reason relations rather than what reason relations are sort of in themselves as they show up in the pure language of conceptual roles, which is implication-space semantics. And in the pragmatics, we presume that we have these determinate reason relations. Where do they come from? How do they get more determinate or better? What's the historical nature of the determination that gets us one set of reason relations? And I think we're farther down the road in talking about the social dimension, but there's things to say about the historical as well. Then I want to address subsentential semantic content. These sentences can just be proposition letters or numerals or something. They have no internal complexity that we care about. They might have a rich type theoretic structure and so on, but it doesn't affect the reason relations. But the sentences do have semantically significant subsentential structure. What makes it semantically significant is something we can cash out in terms of substitution, the effect of substituting one thing for another. That notion of substitution doesn't depend on the sentences actually having parts that you can pull out and plug back in, but what does it depend on? And here I want to say we can go most of the ways to saying how to extend implication-space semantics to deal with semantically significant subsentential structure. We don't have all the pretty results that we'd like, but I'll bring you to the leading edge of our investigation of that. And one of the reasons for that, or one of the things we could hope for from that discussion, is that I observed at the beginning that though our attitude towards imposing structure on reason relations is pretty much anything goes, that is, we would like the expressive power in our rational metavocabularies to handle, to make explicit and talk about, reason relations that are as radically substructural as we can. I mentioned we even can relax the notion of structure that says that it doesn't matter how many times an element occurs in a set, move to a multi-set environment in order to look at relaxing contraction or expansion. Those are Genson's terms. Contraction that would take us from gamma A implies delta to gamma A implies delta, and expansion going the other way around. But still, there is one structure that we want to say it feels as though it's found and unget-overable, and that's between asymmetric implications and symmetrical incompatibilities, just the two of them, one symmetric, one not. And that very structure is reproduced at the subsentential level. There's really just two fundamental kinds of subsentential structure, singular terms, which are by definition symmetrically intersubstitutable, licensed by identity claims concerning the objects referred to, and asymmetrically inferentially significant complex predicates, which are sentence frames. They're, when you're keeping track of the sets of sentences, well, they're identical with sets of sentences that intuitively share the complex predicate, but they stand in fundamentally non-symmetric substitution inferential relations. And that structure is unget-overable in a strong sense. So, for instance, in projective geometry, one allows asymmetric substitution of terms. You've got points, and then you have general points, and whatever is true of a general point is true of all the particular points, but not the other way around. So there's asymmetric substitution relations that the, as it were, singular terms play. So isn't that possible? Well, yes, it is possible, but only at the cost, only at a huge expressive cost. Not all properties are projective properties. You can't reason with a lot of properties in projective geometry, only the very special ones. And that expressive incapacity to reason with a whole lot of properties that you can nonetheless define is an immediate result of trying to relax this picture of symmetrically intersubstitutable terms and then the equivalence classes of the rest of the sentence relative to those substitutions. Well, is it just a coincidence that this same structure that we see at the level of sentences with respect to reason relations gets reproduced when we look to subsentential expressions? Is there some connection between the implication incompatibility distinction and the singular term complex predicate distinction? I don't know, it seems an interesting topic, and I certainly don't know what to say about it. So that's another excuse for looking at how we could take these considerations and go subsentential with them to get, first order logic, say classical logic. We know, Gensen already showed us what a sequent calculus version of classical logic looks like there. Now that involves other features of sequence than our mapping with operations on ranges of subjunctive robustness in the implication spaces goes, but well, that's sort of the next phase of the project, and I will look forward to bringing you as far as we've gotten with that. So these are talking partly about features of the language that we've abstracted from the distinction of social perspective, and then sort of acknowledging, in some sense, an elephant in the room. We're 7 weeks in and we're still doing propositional logic. I mean, would you have thought there was that much to do with propositional logic and just the ordinary connectives, negation and conditional? Well, it turns out, yeah, that's a big topic. And if you count that as a solved problem, because of the nice, neat results that we've got here, the question of, well, what would it look like to extend that to first order languages, ideally with identity? That's a good question. Okay, well, that's what we will be doing going forward. Thank you.